Video 4-2, hydrogen atom line emission spectrum, Bohr model, quantum model, and types of atomic orbitals. Hey, so after that first lecture, you may be wondering, what the heck was all that about? Okay, well, basically, simple basic idea. Waves like light can behave like particles, and particles like electrons can behave like waves. Okay, but where is the electron located? Well, we still don't know. Okay, all we're saying is that, well, it's in an area that has a high probability where the electrons are. Okay, now, where did all these ideas come from? Okay, well, let's take a look at the hydrogen atom line emission spectrum. Okay, when an atom is in its normal state, we call it its ground state. Okay, their electrons will be at their lowest energy levels. Okay, and this is the ground state. Now, if you add energy, the electrons have to absorb the energy and they can't stay there at that lowest energy state. So they have to jump up to a higher energy level. Okay, and now we say that the electrons are in an excited state. Okay, now, the electrons won't stay there. Atoms are basically lazy. Okay, electrons always want to get down to the lowest energy state. So once they jump up there, they're going to want to lose energy. Okay, but to get back down to the lower energy state, they have to give off the energy that they had. So the energy is going to be emitted in the form of light. Okay, and the energy of the light is going to be proportional to the frequency of the light that comes off of it. Okay, so the amount of energy that was absorbed by the electron is going to be exactly the same as the amount that is going to be emitted. Okay, and the more energy that's emitted, the higher the frequency of light is going to be. Okay, so energy comes in. It can be in the form of light, in the form of electricity. Okay, but the electron absorbs it. It can't stay at the ground state at this energy level anymore. Okay, because it now has too much energy. So it jumps up to a higher energy level. Okay, now it can't stay there. So in this excited state, so it's going to lose energy, fall back down again, and in order to come back down again, it has to lose energy in the form of a photon. Okay, energy of the photon is the same as the amount of energy that it just gained. Okay, and the frequency will be equal to E over H. H is Planck's constant. Okay, now, in classical, or what's called Newtonian theory, it says that the electron should be able to absorb any amount of energy and it should be able to jump up to any level, which means when it falls back down, all the possible energy transitions are possible when it falls back down to a lower level. Okay, so the electron could jump up to here and fall back down, or it could jump up to here and fall back down, or someplace higher and fall back down, or someplace in between and fall back down. Okay, it's basically like saying, well, the electron could be here, it could be here, it could be here, it could be here, it could be any place. It's kind of like, think of it like walking up a ramp. When you walk up a ramp, there's no specific place that you have to put your feet. You can put your feet any place along this ramp that you want to. Okay, so this frequency should be given off, this frequency should be able to be given off, this frequency should be able to be given off. So every single frequency possible of light should be able to be given off. Okay. Now, all the frequencies and wavelengths of light should be given off when you give energy to something, which means you should always see white light. Okay. If you analyze this, you should see a continuous spectrum, every single color. Okay. So if you analyze white light through a prism, you see what's called a visible spectrum. Okay. All the frequencies of red, which gradually changes to orange, right, which gradually changes to yellow, etc. Roy G. Biv, right, all the way up to violet. Okay. However, when you take hydrogen gas, put it in a tube, and electrify it, and you guys will see what this looks like when you do the activity in this chapter, it glows. Okay? But it doesn't give off a white light. It gives off a pinkish color light. Okay? And it looks kind of that color. Okay? So What's that telling you? Okay. There's only 4 distinct lines that can be seen, and this is known as a line emission spectrum. Okay. And basically, you get colors here, 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 whoops, here, and here. These colors in between you just kind of ignore. Okay, so how come we don't see a continuous spectrum? Okay, well, a guy named Niels Bohr came along and said, he built on the idea of Rutherford's model that the electrons travel in orbits like planets. Okay, remember, you had the nucleus, and then you had electrons kind of going like that, electrons kind of going like that, and like that. Okay. But what Bohr said was that only certain energy levels are allowed. So the electron cannot exist in between here. It had to be here. Okay. It couldn't exist between another energy level. It had to exist only at a specific energy level. Okay. And the spacing between the energy levels was not equal. Okay. So maybe in elementary school you learned something like this, like you had your nucleus here, and then you had the first energy level for electrons, then you had the second energy level for electrons, and then maybe you had the third energy level for electrons, but the spacing between the first and the second was not going to be the same as the spacing between the second and the third. Okay? They actually get closer to each other the farther away you get from the nucleus. Okay? So, Bohr said the electron could jump up to that level, or that level, or that level, or that level, but only to those levels. It couldn't go in between. Okay? So, it's basically like, instead of walking up a ramp, it's more like walking up a ladder. Okay? The electrons can only jump up to these specific spots. You can only put your foot there, or your foot there, or there, or there. Okay? So, there are 3 series of lines that were observable. Okay? The Lyman series. This is what happens when the electrons jumped up to higher energy levels and fell all the way back down to the ground state. Okay? And what happened when that took place was the photons were in the ultraviolet region. These were pretty high frequency, which also means relatively high energy. Okay? Then there's the Balmer series. These are the ones that you saw. What happened was the electrons started on the ground state, they jumped up to higher energy levels, but they didn't come all the way back down to the ground state. They came back down to the second energy level. Okay? And these will produce those colors that you saw earlier. Okay? Also, there's something known as the Paschen series. They jump up to higher energy levels, but they don't come all the way back down again. They fall back down to the third energy level. Okay? And these, because the gaps got smaller, these are going to be lower in frequency, which also means lower in energy. So they fell into the infrared regions. Okay? And here you see there's actually a couple more possibilities. Okay? So this one here were pretty big. So big, you notice the big energy gaps all the way from up here all the way down here. So the longer the lines, the more energy you have. Yeah, which means you're also going to have high frequencies. So these are in the UVs. Okay. These are in the visible range. Here the lines are getting smaller, so this was in the IR. Here maybe this is going to be in the microwaves. And here, because the line transitions are really small, maybe this is going to be someplace in the radio wave region. Okay. Now the problem was with Bohr's model that it only worked for hydrogen atoms. Hydrogen only has 1 electron in it. Once you put in more than 1 electron, the math just didn't work out anymore. Okay, so what was significant about Bohr's model? Okay, the idea that electrons have to be in specific or quantized energy levels. That was the revolutionary part of Bohr's model. Okay. Now, remember, Bohr said, oh, well, the electrons are going in orbits. We say, nope, they don't do this anymore. Okay. They are in orbitals. Remember, these are the areas that describe a high probability of finding electrons. It's basically an equation, map it out in 3 dimensions, it gives you shape. Okay. Now, each orbital can hold only 2 electrons. So if you have more than 2 electrons, you need more than 1 orbital. Okay. Each energy level can be divided into orbitals. Okay. Above the first energy level, there can be more than one type of orbital, more than one kind of shape. Okay. There can be multiple orbitals with the same energy. Okay. All this stuff will make sense in a little bit, hopefully. Okay. Each orbital repeats in all higher energy levels. So if you get one type of orbital in energy level 1, you'll also get it in energy level 2, same type in energy level 3, energy level 4, etc. Okay. Once you get a specific type of orbital, it repeats itself in all those other higher energy levels. Okay, so what are these orbitals? What do they look like? Okay. 4 basic types of orbitals. The s orbitals, there's only one of them. If you have an s orbital in an energy level, you only got one of them. Okay. It appears in energy level 1, which means it also appears in energy level 2, 3, 4, 5, 6, etc. Okay. It can only hold 2 electrons because there's only one of them. P orbitals, anytime you get p orbitals, you have to get 3 of them. They don't show up until energy level 2. And since each one can hold 2, each one of these can hold 2, the p orbitals can hold 6 electrons. D orbitals, there's 5 different types of them. They only show up in energy level 3. Okay. Each one of those 5 can hold 2, so there's 10. F orbitals, 7 of them. Notice a pattern, 1, 3, 5, 7. Okay. And energy level 2 will have s orbitals and p orbitals. Energy level 3 will have d orbitals, p orbitals, and s orbitals. Energy level 4 will have all those types, s, p's, d's, and f's. Okay, now, remember, orbitals basically define shapes. The shapes are not the shape of the electrons. The shape is like, think of it like the shape of the room that the electron lives in. Okay, page 101 to 103 in your textbook gives you a couple of different examples. Okay, the s orbitals are simple. They're just spherical. Okay, so the nucleus is way really small down here someplace. Okay, on the surface of this sphere, there's a high probability that someplace on the surface, we don't know where, there's up to 2 electrons someplace there. Okay. P orbitals, there's 3 of them, and they basically kind of look like 2 eggs. Okay. These 2 things here make up 1 orbital. Each lobe is still part of the same orbital. So the electrons could be someplace here or someplace here. Okay. And again, we don't care where they are, we just want to know where there's a high probability. What's the difference between each one? The way they're oriented around the nucleus, along x, y, and z axes. Okay. When you put them all together, even though you may only have 1 electron in all 3 of these, remember, are just regions of empty space. They always exist, even if there's no electrons in them. Okay. D orbitals, there's 5 of them. Degenerate basically just means that they all have the same energy to them, even though they have different shapes. Okay. Now, 4 of these have 4 lobes on them, and one of them looks kind of weird. It has the double lobe, kind of like p orbitals, but it has like the little donut thing in the middle there. Okay. And when you put them all together, they kind of look like that. And f orbitals, remember there's 7 of them. Okay. So what happens? Instead of 4 lobes, most of these have 8 lobes to them. Okay. And again, just think of these like the rooms that the electrons can hang out in. Okay. And there's 3 of these things that have the double lobe, but they have the double donut on them. Okay, remember, these orbitals, all they are, regions in space around the nucleus where electrons will probably be found. Okay, even if there's no electrons in them, they still exist. Okay, and the higher the energy level that the orbital is in, the farther away from the nucleus these regions of space will be. So, for review, what was the importance of Bohr's atomic model?